Everybody gets a 0.
What if everyone gets 0? Everyone gets 0.
I'm sorry that you're all cheaters.
It's fine.
Okay, we got to move on. So, right triangle trig is going to capitalize on special right triangle stuff, which you have not seen since you were in 9th grade. So, first and foremost, we have find the values of the 6 trig functions of theta in a given figure. So this is very basic geometry stuff. You'll be able to do this just by SOHCAHTOA. So this whole first section is SOHCAHTOA. Although we do need to find the missing side. How do we find the missing side? We've got a 12 and a 5. Pythagorean theorem, so 12 squared plus 5 squared, right, equals hypotenuse squared. So that's going to be 169 equals h squared, so h is 13. There are certain Pythagorean triplets you should be familiar with. 5, 12, 13 is one of them. So if you see legs of 5 and 12, then there's 13 without even any thought. If you double 10, 24, 26, any ratio of 5, 12, 13 is one family. 3, 4, 5 triangles. Any ratio of that. 6, 8, 10, 9, 12, 15. Anybody know any others? There's one more. Yep. Oh, is it 12? Hold on, there's one more. 8, 15, 17 is one. There is a 24. I can't think if it's 5 squared plus 24 squared. Nope. 7, 24, 25 maybe. Yeah. 7, 24, 25. I mean, there's a limitless number of these, but these are the most common ones. Really, honestly, those two are the most common ones.
Isn't it any multiple of those?
Yes, yep. So we would talk about the 5, 12, 13 right triangle family, which would be 10, 24, 26, and so on. I already mentioned that. Okay. So once you get that, your sine of theta is going to be the opposite over hypotenuse, 5/13. Cosine is going to be adjacent over hypotenuse, 12/13. And tangent is going to be opposite over adjacent, 5/12. Your other 3 are just going to come from the reciprocals like we did yesterday. So I'm not going to go into detail on that. B is a little bit more challenging because it's not a Pythagorean triple, but you're just going to set up 1 squared plus b squared equals 3 squared. Subtract your 1 from both sides. B squared is going to equal 8. Square root of both sides, and the square root of 8 reduces to 2 root 2. And then again, go through your sine, cosine, and tangent. Reciprocate all of those. Rationalize if necessary. That's all review. Yes? Okay. Special right triangles. Okay? 30, 60, 90s are special right triangles. And 45, 45, 90s are as well. With, I'm trying to think, I could explain this in like 3 different ways, and you guys have enough background information to know it. But let's do 45, 45, 90 first. Because this is x, what's the other leg? X. So that's just from the isosceles part. Does anyone have memorized what the hypotenuse then is? X root 2, correct. Now, if you didn't know that, this one is one that you can sort of derive on your own from the Pythagorean theorem again. X squared plus x squared equals hypotenuse squared. And you get 2x squared equals hypotenuse squared, square root both sides, and so h equals x root 2 when you reduce that radical. Yes? Okay? So if you don't memorize that one, we still have it, but it goes x, x, x root 2. 45, 45, 90. Now, from another vantage point, since we especially did this yesterday, what's the cosine of 45? Based on what we did yesterday, that's the one value they want you to have memorized is root 2 over 2. This is also going to show that happening, because if you take the cosine of 45 and you do the adjacent x over the hypotenuse x root 2, that's going to reduce to 1 over root 2, which rationalizes to the root 2 over 2 that we derived yesterday, derived from a totally different angle, right? Yet both of them were derived using the Pythagorean theorem. This is just the Pythagorean theorem in a right triangle, just labeled 45, 45, 90. Yesterday it was in the unit circle with that AA point and then the Pythagorean theorem. But either way you look at it, the cosine of 45 is root 2 over 2, the tangent of 45 is root 2 over 2, the sine is 45 is root 2 over 2, and the tangent comes from the opposite over the adjacent, which of course is something over itself, 1. Tangent of 45 is 1, right? The 30, 60, 90 is a little bit more, you can't really derive it on your own from the same perspective we did this one because we only have one side. This one you just have to know. If you know the shortest leg is x, what's the hypotenuse? Do you remember? 2x, good. What's the other leg? Very good, x root 3. So this for 30, 60, 90 will be x root 3, and 2x. And this is really why we memorize the 45-degree angles, the 30-degree angles, the 60-degree angles, because we know these special right triangle relationships. So now when we look for the sine of 30, we can do the opposite of x over the hypotenuse 2x, and that reduces to 1/2. That, and no matter what triangle you're in, these ratios, if it's a 30, 60, 90, hold true. So we'll always get the sine of 30 to be 1/2. This is where those numbers, people didn't pick, memorize these angles just because. They didn't pick those out of thin air. They decided that those angles are the most prominent ones because of these special right triangles. So this would get us the sine, cosine, and tangent of 30, as well as the sine, cosine, and tangent of 60. Yes? You can't really do the sine, cosine, and tangent of 90 or 0 in this way because then we'd lose it. We don't have, like, for the 90-degree angle, our opposite is our hypotenuse, and that kind of is a conflict. So it really, this whole SOHCAHTOA thought process is only used for 30s, 45s, and 60s. 0-degree angles and 90-degree angles are always going to have the logic of the unit circle. 1, 0, so that's the sine, that's the cosine of a 0-degree angle. On a 90-degree angle, there's your sine, there's your cosine. On a 180-degree angle, there's your sine, there's your cosine, and your tangent comes from y over x. So for your zeros and 90-degree reference angles, we're going to still go back to our unit circle on that, logically, because SOHCAHTOA doesn't make much sense. So are there any questions on that? Okay, so here starts the process of you need to memorize these values. I'm going to add 0-degree and 90-degree. We use, like I said, we use the unit circle for those. And so those we can do pretty quickly right here. Sine is the y-coordinate, right? So on a 0-degree angle, the y-coordinate is 0. So the sine of 0 is 0. On a 0-degree angle, the cosine is your x-coordinate, so that's 1. And on a tangent, it's the y-coordinate divided by the x-coordinate, so that's still 0. If we go to our 90-degree angles, take your y-coordinate as your sine, 1. Take your x-coordinate as your cosine, 0. And your tangent is the y-coordinate of 1 divided by the x-coordinate of 0. That's undefined. Sine of 30, we kind of already showed the opposite over hypotenuse ratio there. If you look quickly at the sine of 45, it's going to be opposite over hypotenuse, that's going to be 1 over root 2, which rationalizes to root 2 over 2. We already talked about that. And a 60-degree angle, if you look at the opposite, x root 3 over hypotenuse 2x, that's going to reduce to root 3 over 2. And there's your sine column. We would do the same with the cosine and the same with the tangent. Actually, the tangent, we can look at the triangles and do opposite over adjacent, or we can look at our sine and cosine columns and just do the sine divided by the cosine will give us that tangent. This sine divided by the cosine will give us that tangent, and so on. Or you can think of your triangles and do opposite over adjacent. This all if you want to explain why these values are what they are. But you should memorize them. Did Mrs. Ziggy show you the pattern here? Okay, so, and you should, but if you're ever failing at that, this is root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Did you ever know that? Well, that's just it. So if you're truly memorizing them, you shouldn't have any intermediate thought process. That's what memorization is, right? So to truly memorize them, she's right. You shouldn't have time to think this through. But, you know, in reality on a test, no one can prevent you from doing that. The reason we want you to memorize it is because as I'm talking about things, and I say, oh, yeah, the sine of 60 is root 3 over 2, you should just, you know, kind of accept that as fact and move forward. You shouldn't have to think, wait a minute, how'd she get that so fast, right? Because you're going through this intermediate thought process. So that's really that. So we can be more fluent and we can really focus on the concept that we're dealing with versus getting caught up on, wait, is that the right value for sine? Okay, and that's really the reason. But I do want to show you that root 0 over 2, root 1 over 2 would simplify to that. Root 2 over 2 is what it is. Root 3 over 2 is what it is. Root 4 over 2, of course, reduces to 2 over 2, which is just 1. And the cosine column is completely backwards. So 0, 1/2, root 2 over 2, root 3 over 2, and root 4 over 2, which is 1. With tangent, most people are pretty good of the tangent of 45 is 1. And then one of these is root 3 and the other one is root 3 over 3. And sometimes I can remember myself as a student always getting that confused, which one is which. This column increases from smallest to biggest. So if you have to choose between root 3 and root 3 divided by 3, this one's the root 3 divided by 3 because that's a smaller number. And it's gradually increasing. And then this is just plain old root 3. Any questions on that? Memorize them. Yeah, and for Algebra 2, I mean, I do show my kids this. To be honest, though, the number of times that you go back and you really think about how they came about is not often. I do agree it's helpful to see, but they all come from special right triangles. So it's all kind of a geometry tie-in. Now with the cofunctions, do we know what a cofunction is? Like sine and cosines are cofunctions of each other. That's because the sine of an angle is the same as the cosine of its complement. So that we're going to write that by putting 90 minus theta, right? Because these complements are two angles that add up to 90. So if one angle is theta, the other one you would get the other one by doing 90 minus whatever that theta is. And look, you can see it just with our, like the sine of 0 is 0. That means the cosine of 90 is the same thing. The sine of 0 equals the cosine of 90 because those are complements. The sine of 50, even though we don't know that value, is going to be the same as the cosine of 40 because they're complements. You can see the sine of 30 is the same as the cosine of 60. Sine of 30, same as the cosine of 60. It's interrelated with the fact that these columns are backwards versions of each other. Tangents and cotangents work the same way. Secants and cosecants work the same way. Because we've memorized the sine and cosine values, it's easiest to see with those, but the same is true for tangents and cotangents, and the same is true for secants and cosecants. Now, I just presented that in degrees. There, so 90 degrees, 90 degrees, 90 degrees. The same is true in radians as well. So that would be the cosine of what's 90 degrees in radians. So if you see it written, you know, if it's the rule is presented in terms of radians, it's going to be written pi over 2 minus theta is going to be considered the complement. Any questions? Okay. So on the back here, find the cofunction. I just kind of did a bunch of these on the front. This is equivalent to the cosine of 18 degrees. Cosecant has the cofunction of secant, right? What is the complement to pi over 3? So that would be pi over 2 minus pi over 3, which is, get a common denominator, 3 pi over 6 minus 2 pi over 6. So what's that? Pi over 6. Now, I don't encourage this, but just to make full sense of it, for those of you who like to change things to degrees, pi over 3 is a 60-degree angle, and pi over 6 is a 30-degree angle. So cosecant of 60 degrees equals secant of 30 degrees. Makes sense. Stephen? No, if it starts in radians, keep it in radians. You wouldn't say cosecant of pi over 3 equals the secant of 30 degrees. But your final answer, I mean, I can't prevent you from doing that. All I can tell you is you may run out of time. If you fight thinking in radians, you may run out of time. Not necessarily on this problem. It's an additional 2 seconds. But as we move forward and we're getting into a deeper level of this stuff, if you've been fighting thinking in radians and you've translated everything to degrees, what we are about to get into is going to be a lot harder and a lot more time consuming, and it's not going to go well. So you have to just, think in radians and really just train yourself to do it until you're comfortable. But if it's in degrees, keep it in degrees. If it's in radians, keep your answer in radians. That's just the general rule for all of trig. Okay? I don't know what that squiggly mark is. I must have accidentally written on it before I threw it through the copier. But anyway, a surveyor measured the angle of elevation. Do you remember angle of elevation? To the top of a building. So here's my building. Bunch of windows. My angle of elevation, I'm a little person on the ground. Your angle of elevation is the angle made with your line of sight to the top of the building and just kind of the straightforward line of sight. So that angle of elevation is right here. It's 22 degrees. The transit, do you know what the transit is? Does anyone know what a transit is? It's kind of that tool that is used. So I'm not going to do a person. It's kind of like a tripod that like surveyors use, engineers on construction sites. No? Okay, well, that tool is called a transit. Is 5 feet above the ground. So this line of sight is coming from the transit. That's also 5 feet off the ground, is what they're saying there. There's a distance of 5 feet on top of this. So our building actually comes down 5 additional feet. The transit is 5 feet above the ground and 300 feet away from the building. So we're going to call this 300. So then we're going to use some basic trig geometry type trig to find the height of the building. But we have to find this portion of the height of the building first, and then we'll add 5 on at the end. Does that make sense? So are we going to use sine, cosine, or tangent based on the sides we know and the sides we're trying to find out? Tangent. You always take the tangent of an angle equals the opposite side is our x over our adjacent side is 300, and of course we need a calculator for this because no one knows the tangent of 22. What mode should our calculator be in? This is going to be a popular issue this chapter because sometimes we're in degrees and sometimes we're in radians. What's the problem written in? Degrees. So you should have your mode in degrees, and you may often be switching back and forth. Okay, there again, I think, is a calculator section. If there's not a calculator section, then we would make that a 30-degree angle, or a 45 or a 60, so that you can do it without a calculator. Does that make sense? But get it in degrees. We're going to take the tangent of 22, and we're solving for x, so multiply it by 300 on both sides. And we get 121.2 to say to the nearest anything. Of course not. 121, we'll go to the nearest tenth. 121.2 is our x value. So what's the height of the building? 126.2. Simple geometry type stuff there. On the next one, a building 21 meters tall casts a shadow 25 meters long. Where's the sun? Yeah, where? I always like to visualize that. The sun's coming down, the building blocks and creates a shadow. Find the angle of depression. So the angle of depression from the sun. So here's our sun, is right at the tip here, we'll assume. The angle of depression is the angle looking down, formed with the horizontal line of sight. Did you know that? So the angle of depression isn't actually in the triangle. It's right here. But because this is parallel, think geometry, the angle of depression from the top side looking down is going to be the same as the angle of elevation from the bottom looking up. Is that clear? Because of alternate interior angles. So we are essentially finding this. So do we want to use sine, cosine, or tangent? We know the opposite, we know the adjacent. So the tangent of x equals opposite over adjacent. Now, it didn't say in degrees or radians, so I'll just assume we'll stay in degrees here. Do you remember how to do this on your calculator to find the value of x? Inverse tangent, correct. So to get rid of tangent, you do inverse on both sides. You don't divide by tangent. I hate that. People divide by tangent. Tangent's not a number. It's a functionality. That would be like dividing by log on both sides. You don't do that, right? So we inverse tangent. And don't we inverse log too? What's the same as inverse logging? Exponentiating. Good. So we get approximately 40 degrees. Okie doke. Despite our conversation, we managed to have